Throughout history, human innovation has been a story of evolution, a journey driven by our needs and aspirations. Rarely do we get it right in the first place. Instead, we refine, reimagine, and reinvent, turning simple ideas into extraordinary creations. Hi everyone, this is Nashid, and welcome to day 2 of 100 Days to Understand ChatGPT Architecture. Consider the humble beginning of the wheel. In dawn of civilization, early humans didn't immediately envision the revolutionary tool. It was a gradual process sparked by necessity. Perhaps to move objects around more efficiently or to travel faster across the vast landscape. From those first crude wheels, carved from the stone, we have journeyed to an era of sleek cars, massive airplanes, and even rovers exploring distant planets. Each step an iteration, an innovation, and response to challenge, a dream or a necessity. This story of progression isn't just confined to the physical inventions, but it is mirrored through the realm of ideas and technology, particularly in the field of artificial intelligence. The evolution of the neural network, from basic models to sophisticated architectures such as transformers, echo this very human journey of innovation. In today's video, we'll explore this fascinating evolution. How did we move from a simple neural structure to a complex model that can understand languages? And not just confining to the languages itself, but even recognizing images and transforming the industries. Let's begin with the caveman's era of AI, where people used to write if-else statements for any condition-based operation. Slowly, the humans understood that there's a limitation to how many if-else statements could be written by a human. Enter the era of data science and machine learning. We tried to solve more complex problems by, put it in another way, thousands of if-else statements and some machine learning algorithms. But these ML algorithms did have their own limitations. Enter the era of neural networks and deep learnings. In the beginning, neural networks were fairly simple structures, and these were the early days of artificial intelligence, where we just focused on creating models that could mimic basic human cognitive functions. Feed-forward neural networks are the simplest form of artificial neural networks, where you could imagine it in this way, that it's a one-way street where information travels in one direction, from the input layer through the hidden layer, and finally to the output layer. The beauty of these networks lied in their simplicity. They consist of input nodes or neurons that receive data, and each connection between these neurons has weights. And when these weights are adjusted during the learning process, the data travels through the network, getting them transformed at each layer, and then it finally reaches the output layer. Despite of these simplicities, the feed-forward neural networks were very crucial in the early applications such as basic image recognition and classification tasks. But they had their own limitations, especially when it came to more complex tasks. One of the major limitations was the inability to process sequential or temporal data. Think about maybe a language. Understanding a sentence isn't just about individual words, but it is also about the order and the context. Feed-forward neural network couldn't grasp these sequential aspects, leading researchers to explore new architectures. And this exploration led to the birth of a new kind of neural network, which could handle sequential data and remember the past information. Enter the era of recurrent neural networks, or also known as RNNs. These RNNs marked a significant leap in understanding the neural network design. Unlike the feed-forward predecessors, RNNs have loop in them, allowing information to persist. In looping mechanism is what makes RNNs special, allowing them to remember the previous information in the network, a critical feature for tasks like language processing, where understanding the context is the key. The RNN showed great promise in the area like speech recognition, language modeling, or even text generation. They were better equipped to handle sequence and offer more dynamic approach to the neural network. However, RNNs weren't with their own flaws. One significant issue that were faced by the researchers during training the RNNs was the vanishing gradient problem. As such, the network learns using gradient, and these gradient parameters guiding the learning process can become exceedingly small, virtually halting the learning process. This problem made training deep RNNs extremely challenging, limiting their effectiveness in capturing long-range dependencies in the data. Essentially, RNNs struggle to remember information from the distance part in a sequence, a major hurdle for complex sequence processing tasks. The limitations of the RNN spurred further innovation, leading to more advanced architectures like long-term LSTMs or long short-term memory networks. These sought to overcome hurdles that were faced by RNNs. Now let's just deep dive into LSTMs then. LSTMs were designed to address a key shortcoming of the traditional RNNs, particularly the vanishing gradient problem. They do it by a unique architecture that includes something called gates. RNNs have three types of gates: the input gate, the output gate, and the forget gate. These gates control the flow of the information, and they decided what information had to be retained and what had to be discarded, making LSTMs capable of learning which data is important to keep for the long-term memory and what to forget. This ability made LSTMs incredibly effective for complex tasks such as language translations, speech recognitions, and even composing music. They were game changer for how neural network process information in a sequential data. However, LSTMs were with their own limitations. Despite of the improved memory capacities, they struggled with processing very long sequences. And due to this, the gradual loss of information over time was inevitable. Moreover, LSTMs are computationally expensive. So their complex architecture means that they require a significant computational resource, leading to longer training times. This became notably a challenge when dealing with large data sets or even trying to scale up the application. This limitation of LSTM, while fewer than the RNNs, led to further innovation of neural network design, and this was the stage which was set for the introduction of attention mechanism, and eventually the transformer model, of course. But there's more. But before we jump to the transformers, there's one more model one more architecture that I would like to introduce, which were the GRUs. These gated recurrent units, or GRUs, were an evolution from the LSTMs and RNN models. They introduced simplicity, and they removed the complex structures of the LSTMs while retaining their ability to process sequential data efficiently. GRUs streamlined the idea of gate in the LSTMs. They combined the input and forget gate into a single gate known as update gate, and also known as the reset gate. These modifications made GRU less complex and faster to train than the LSTMs. While they were effective in capturing the dependencies of the sequence, GRUs came with their own problems. They excelled for language modeling and speech-to-text applications, but often were very inefficient. They were very inefficient with a larger data set. While they were more efficient than the LSTMs, sometimes they would fail in a high complex data structures. Furthermore, the simplification of the GRUs, while beneficial for speed and efficiency, can sometimes lead to the reduced model expressiveness compared to the LSTMs. This means in certain scenarios, especially when nuanced understanding of the data was critical, LSTMs actually outperformed GRUs. The development of GRUs represented a balance between the complexity and efficiency of the neural network design, yet the quest for the most effective architecture continued, leading to the emergence of attention mechanism and the revolutionary transformer architecture. Now, of course, it's very exciting to hear about the transformer architecture ultimately, but we will dwell this on our day 3. Excited? Well, see you tomorrow then.